Thanks for the introduction. Hello, everyone. I'm Yupeng Zhang from the University of Maryland. Today, I'm going to present our paper, vSQL, Verifying Arbitrary SQL Queries over Dynamic Outsourced Databases. This is a joint work with Daniel, Jonathan, Dimitris, and Babis. So, cloud computing is widely used in practice, and everyone is delegating their data and computation to servers in the cloud. All big companies like Amazon, Oracle, and Google are providing this database as a service in cloud computing. It enables the client to delegate the storage of a database to a cloud server, and later she can issue a SQL database queries and fetch the results from the server. This provides great benefits to end users. For example, it can reduce the local storage and computational consumption. However, despite of these great benefits, it also raises new security challenges. And one of them is called integrity. Namely, how can we make sure that the result returned by the server is indeed computed by this query on the database I outsourced before? So this is something different from privacy. So in some scenarios, it's okay to let the server know the content of the database, but in this scenario, we want to make sure that the result is correct. That's called integrity. The crypto solution to this problem is called verifiable computation. In particular, it's verifiable databases. It allows the client to compute a short digest from the database, stores it locally, and also outsources the database. Later, for a SQL query, the server returns the result plus a proof. And with verifiable databases, the client is able to validate the correctness of the result using the digest and the proof. And the security guarantees that even if the server is malicious, it is infeasible for him to return a wrong answer, but still passes the verification. In verifiable computation, we are interested in the following efficiency measures. First, setup time. This is the time to compute the digest, and ideally, we want it to be linear to the size of the database. We also want to reduce the prover time, which is the overhead for the server to generate the proof. And then we have proof size and verification time. We want them to be as small as possible. There are a lot of great prior work in the literature of verifiable computation, and they can be roughly classified into two categories. The first one is called customized approach, and the representing example is called authenticated data structures, ADS. For example, there are a lot of work supporting range queries, multi-range, and join queries individually. And the good thing about this approach is that it's usually very efficient. But the drawback is that it only supports limited operations, and that's why it's called customized approach. So if we draw a plot where the x-axis represents the efficiency and the y-axis represents the expressiveness, this work can be placed on the bottom right. On this line of work, there's a system called IntegrityDB that integrates different types of authenticated data structures and supports a subset of SQL queries. In this paper, we're going to compare our system to this one, and it can be placed here. The next category is called generic approach. An example is snarks. In principle, snarks can support all possible functions that can be modeled as arithmetic circuits, which are circuits with addition and multiplication gates. Plus, it always generates constant size proof, and the verification time is very fast. But the problem is that usually it introduces a big overhead on the setup time and prover time. In addition, it needs a function-specific setup phase. For each function you want to support, you need to pre-process separately. This is not good if we want to apply snarks to verifiable database, because there are so many types of SQL queries, and we do not want to pre-process them individually. Back to the plot, snark can be placed here. So in this paper, we are proposing a new verifiable database system called vSQL, and it can be placed at this location. As you can see, the expressiveness is almost the same as Snark, and in particular, we can support arbitrary SQL queries. In the meantime, the efficiency is comparable to a customized approach and is much faster than Snark. Finally, we can also support, we don't have a function-specific setup phase. Concretely speaking, here's the SQL query we see in practice. As you can see, there's a lot of subqueries and complicated nesting in it, and taking me some time to fit it into a single slide. This is a query from a benchmark called TPCH, which is widely used in the database community to test the performance of new database systems. And in our paper, we can support this type of queries on databases with millions of records and tens of rows, tens of columns. So next, our construction. So the first thing I want to show you is a major building block of our system called interactive proof. As a cryptographer, when you see a complex query like this, you model it as a circuit. Okay? The circuit takes the database as the input and outputs the result of the query. And we want the server to tell us what is this result. First, we want to define a polynomial f in x by the input database. By define, you can think about it as every coefficient of this polynomial is an element from the database. Okay, so in this way, the size of this polynomial is the same as the size of the database. For those who are familiar with interactive proof, this is called multilinear extension or low-degree extension. Similarly, we define polynomials by the values in wires of every layer in a circuit, like this. In this way, we have a well-defined relationship between the polynomials in two consecutive layers, because they are connected by circuits of addition and multiplication gates. So even if we define things in this way, you cannot ask the server to tell you what are these polynomials and check the relationship, because it will be even slower than evaluating the circuit yourself. Fortunately, we have a way to check the relationship between two polynomials at a random point. And using this technique, here's the protocol for interactive proof. The client and server have the input and the function model as a circuit. The server first sends a claimed output to the client, which is not trusted and is in red on the slide. From the output, the client compute a polynomial f out and evaluate it at a random point r out. After that, the client sends a random challenge to the server, and the server returns the f1 r1 to the client. Note that here, this is the constant size. It's just a single number representing the evaluation. And then use the technique, the client can check the relationship between f out r out and f1 r1. In this way, it reduces the correctness of the output to a value for one layer above. Similarly, they repeat the process layer by layer, and at the end of the protocol, the client receives a claim about the input layer. And the reduction says that if this value f in r in is correct, the output is correct. How can she make sure this? We require that the client should store the input locally and computes this f in r in on her own and checks they're indeed equivalent. This completes the whole reduction and guarantees that the output is correct. And that's the whole protocol of interactive proof. This might be a little bit technical, and if you didn't follow the whole protocol, what you need to keep in mind is that interactive proof is a way to reduce the correctness of the output to a claim about input. So if we want to use IP for verifiable databases, the benefits are there's no setup time. They begin right away. And the prover time is very fast because it only involves simple addition and multiplications. There's no heavy crypto operations like exponentiation or bilinear pairing. But it is not quite working because we require the client to store the whole database locally. As at the last step, the client needs to evaluate a polynomial defined by the output at the random point. So in our paper, we further propose a protocol for verifiable polynomial delegation, VPD. This protocol enables the client to compute a short digest for a polynomial and then sends the polynomial to the server. Later, the client can issue a query for evaluating the polynomial at point A. The server returns f of a plus a proof, and the client is able to check that this is indeed the correct evaluation f of a. With this protocol, we can further delegate the last step of IP to the server side. And here's the whole protocol for our system. The client has a database. It defines a polynomial f in x, and the client will first use our VPD protocol to compute a digest and delegates the database. When issuing a SQL query that is modeled as a circuit, the server returns a claimed result. With this result, the client and server can initiate an interactive proof. And at the end of this, the client receives the claimed value for f in r in. This is the IP part. After that, the client uses our VPD protocol to further delegate the task to the server to ask about what is f in r in, and use the protocol to validate this correctness. This is the VPD part. Finally, the client checks these two values are equivalent. This completes the last step of IP and guarantees that the result is correctly computed. So in this way, we solve the problem of storing the database locally. In addition, we also propose a way to support something called auxiliary input. To motivate it a little bit, some functions are hard to compute using arithmetic circuits. For example, division. But they are very easy to verify if you have some hints from the server. If the server tells you the quotient q and the remainder r, you can check that a is equal to q times b plus r, using one multiplication and one addition. That's why auxiliary input is useful, but interactive proof cannot support it. Again, because at the last step, the client needs to access the whole input. So in our paper, we support auxiliary input using the exactly same construction, verifiable polynomial delegation, in a slightly different way. Here, we also allow the server to have a polynomial in his mind and commits to this polynomial by sending the digest to the client. Later, the client issues an evaluation query, and the server returns f of a plus a proof. And the client can check that this is indeed the correct f of a for that polynomial the server commits in the first place. With this, the server can commit to the inputs to the circuit without sending them back. It only needs to send a constant-sized digest. So with all these techniques, we have a verifiable system that supports that only have setup phase for the database, but not for any queries. The approval time is very fast because we only have crypto operations for the database in the VPD protocol. We support auxiliary input, and in addition, we can support dynamic database with expressive SQL updates. Finally, I want to show you some experimental results. First, comparison with prior work. We run the systems on queries and databases from the TPCH benchmark. And in particular, the largest table in the database has 6 million rows and 13 columns in it. And here's the performance for query number 19, which is the one I showed you before on the slide. For setup, it takes 7 hours for IntegrityDB, approximately 100 hours for Snark, and 0.7 hour for our system. For the approval time, it takes 1.8 hours for IntegrityDB, 54 hours for Snark, and 1.3 hours for vSQL. As you can see, we're even a little bit faster than IntegrityDB, which is a customized approach supporting only a subset of SQL query, and much faster than Snark. For verification time and communication, which is the proof size, we are a little bit better than IntegrityDB and much worse than Snark. But as you can see, the verification time is always below 1 second, and the communication is always tens of kilobytes, which are not bottleneck in practice. the performance for another query. This is not supported by IntelliDB and takes more than 300 hours for Snark to set up. But in our system, for the same database, we don't need to set up again. For prover time, we are more than 100 times faster than Snark, and we are worse in verification and communication. In a follow-up work, we can further reduce the setup time and prover time of our system by at least 4 times. Next, I want to show you some results for updates. In TPCH, there is a query to create a new table on the fly. The size of the old table is 2.8 gigabytes, and the size of the new table is still 1.7 megabytes. And here's the performance of our system. As you can see, the prover takes half an hour, the verification takes tens of milliseconds, but most importantly, the total communication is only 85 kilobytes, which means neither of the old table nor the new table is ever transmitted back to the client. But the client still can make sure that this table is correctly generated and can even run other SQL queries on the new table verifiably without even accessing the new table. That's the power of expressive SQL updates. So to sum up, in the theory side, we propose a protocol for verifiable polynomial delegation. Using it together with interactive proof, we have a verifiable database system that can support delegation of the database, auxiliary inputs. We have no query-specific preprocessing, and we can support expressive updates. On the system side, we show that our prover time is comparable to a customized VC, and setup time is much faster, and we have a much better expressiveness. Compared to Snarks, we improve the efficiency by orders of magnitude. That's all of my talk. Thank you.
Ben Fuller, UConn. A couple of questions if nobody else comes up. It seems like your approach is inherently not concurrent, whereas Snark, like it's a single message, you don't need to worry about concurrency.
You're saying the interactive.
Yeah.
So you can use the Fiat-Shamir heuristic to reduce this to non-interactive using random oracle.
And you don't have any problems with your VPD protocol?
No, that one is, again, a single message thing.
Okay.
So you do not even need an extra round for that protocol. Okay. Just send it right back.
And can you give a hint on how you handle dynamism? Because it seems like your digest is fixed for...
Mr. Dynamic...
how you handle updates.
Yeah, because the output of the circuit can also be a commitment. So what you need from the output is a random evaluation. So the server just sends you a commitment of the output. You use the VPD again to get the random point, and then completes the whole protocol. So in this way, you get a new commitment for a new database.
Thank you.
Hi, very nice work.
Thank you.
I think early on you said that there was some reduction in expressiveness with your system with respect to Snark. Mm-hmm. Can you speak to like what specifically you're referring to?
Oh, you mean the slight difference?
Yeah, like what sorts of things can't you do, with your system as opposed to
yeah, so actually it's kind of depends on the efficiency. So interactive proof is in particular efficient if the circuit is regular or can be represented as a data parallel circuit. Mm-hmm. So for these things, we can get such good numbers. And when we use it for verifiable database, those SQL queries are inherently data parallel. Mm-hmm. But if the circuit is like totally random, we can still run the protocol, but the efficiency might be harmed a little bit. So that's why I'm saying this. It's a little bit difference between Snark and our system.
Did you come across sort of elements of sort of supporting SQL that were that sort of were inefficient in that way, or were you able to sort of find?
Actually, no, because if you think about SQL language, when you issue this SQL query, you do not even know what is the database, which means the SQL query is a succinct representation and will be run on every row of the database, no matter how many rows are there, which means unless you express your SQL query as large as a database, otherwise it's inherently data parallel.
Okay, thank you.
Okay, so let's thank the speaker again.
Thank you.